What are scalars and vectors? Why do we need them? And where do we use them? In order to understand them, let's begin. By definition, scalars are those physical quantities which require only magnitude for their complete descriptions or complete meaning. It means scalars require only magnitude. Whereas by definition, vectors are those physical quantities which require both magnitude and direction for complete description. So they require both magnitude and direction. Let's see some examples. Example of scalar quantities are length, area, volume, mass, energy, density, charge, pressure, etc. Whereas some examples of vector quantities are velocity, displacement, acceleration, electric field, magnetic field, etc. Now we'll understand them in detail. Cambridge University is about 20 kilometers from London, 20 degrees east of north. If a person travels from London to Cambridge or from Cambridge to London, no matter what the direction may be, the distance between London and Cambridge is always 20 kilometers. So here, in order to describe distance, we need only magnitude. So distance is scalar quantity. Let's see another example here. We have a ball whose mass is 2 kg. Whatever be the direction, either in this direction or in this direction or in this direction, the mass of ball is always 2 kg. So here again, the direction doesn't play an important role here. In order to give the complete meaning of mass, we just need magnitude, which is 2 kg. So mass is a scalar quantity. Let us see some other examples here. Let us consider a block whose mass is, let be 2 kg, is acted upon by a force F, let it be 5 Newton. If we consider this direction to be positive, then of course the opposite direction is negative. So here, if the force is applied in this direction, the object or the block will move here. If the force was applied in this direction, the block would move here. If the force was applied in this direction, the block would move here. Here the force, when we talk about force, only magnitude is not enough here. The direction also plays an important role here. So force is a vector quantity because force needs magnitude and direction. In the direction which the force is applied, the movement is in the same direction. So here force is a vector quantity. Here the movement of the block is in a straight line. Whereas the movement being in a straight line, we can call it as a displacement. The motion of the block is in this direction. Here the block moves from left to right, which we have considered as a positive direction, and velocity is displacement over time. So if block moves from left to right, the velocity is positive because the displacement is positive. If the block moves from here to here, that is right to left, the direction is opposite. Thereby the velocity will be negative because the displacement is negative. Here displacement is some kind of vector form of distance. Displacement is considered as the shortest path, so it has to be in a straight line. Here the displacement doesn't only need magnitude, being what displacement it has covered. The direction is also important because the body moves from left to right or from right to left. Thereby displacement is also a vector quantity. So there is a beautiful question here. Should a quantity having magnitude and direction be necessarily a vector? Give some examples. By definition we have read, vectors are those quantities which have magnitude and direction. But is the vice versa true? Always true? If a physical quantity have magnitude and direction both, does it have to be necessarily vectors? The answer is no. Why is it so? Let us consider an example of electric current. Electric current is not a vector quantity, but it has magnitude and direction. The direction always being positive to negative terminal. So if it has magnitude and direction, which is from this terminal to this terminal, why is it not a vector quantity? Well, electric current has magnitude and direction, but it doesn't follow the important law of vector addition. In order to be a vector quantity, it has to follow law of vector addition. Same is the case with higher angles. Higher angles have both magnitude and direction. Higher angles have both magnitude and direction, but even though they are not vector quantities, because it doesn't follow law of vector addition. So the important point to note is here, vector quantities always have magnitude and direction, but if the quantities have magnitude and direction, they are not necessarily vectors. We have seen example here where electric current and higher angles have both magnitude and direction, but they are not vector quantities because they do not follow vector law of addition. Now we have known what are vectors. How do we graphically represent them? Well, generally vectors are represented in this format. Capital letter with arrow on the top, small letters with arrow on the top. Let us take an example. We have a starting point, we have a line segment and arrow. Let it be O and this be P. Now this line segment is OP. Now this line segment OP represents a vector of a magnitude which is proportional to its length. Now whatever be its length is the magnitude of this vector. Now this vector may be represented by A caps or A or even by the name of the line segment. The line segment being OP, so it can be represented by OP with arrow over its head. Now this length gives the magnitude of the vector OP. Now we need direction as well. In order to get the direction, we must have a standard reference point or line. By definition, vectors have both magnitude and direction. First of all, we'll deal with magnitude. Let us take an example of a vector of force F 10 Newton. Now we know 10 Newton is the magnitude of the force, whereas we don't know the direction yet. Now we are interested in magnitude itself, not in the direction right now. So the magnitude is the length of the vector itself. In order to replace 10 Newton, we can do 1 centimeter equal to 1 Newton, which will be replaced by 10 centimeter long line segment. Sometimes the number can be huge, so it's better in proportion. So here we'll replace 1 centimeter equal to 2 Newton. So for 10 Newton we need 5 centimeter. We have a starting point, then we need 5 centimeter. And arrow. Let it be OP vector F. Now we know the scale. 1 centimeter is equal to 2 Newton. So this 5 centimeter will represent 10 Newton. The length is proportional to the magnitude. Now is the time for the direction. In order to plot a direction, we need a standard reference system. It can be one-dimensional, or it can be two-dimensional, or it can be three-dimensional. We'll restrict ourselves to two-dimension only. This is a two-dimensional Cartesian coordinate system. This is x-axis, this is y-axis. Now we'll fully define our vector. Vector F is equal to 10 Newton, 45 degree of x-axis. We know the direction anti-clockwise of x-axis is always positive. So we have 45 degree, which is positive angle. So the 45 degree has to be in the center. Let this be O, let this be P, and this length to be 5 centimeter. Now this angle has to be 45 degree because this is positive angle anti-clockwise of x-axis. So in this way we can represent a vector. So in this way we can plot a vector on a graph. So on a graph on a 2D plane, this being origin, this being x-axis, and this being y-axis. We have seen our force F equal to 10 Newton, 45 degree of x-axis. So this is our two-dimensional plane. We'll keep the tail of the vector at origin, this being origin. This is our tail of the vector. Here we have defined 1 centimeter is equal to 2 Newton, which is the scaling or proportionality for the length of the line segment. So we need 5 centimeter for 10 Newton. So what we can do is we can take an compass, put one in here at the origin, and draw an arc whose length has to be 5 centimeter. Now this arc of 5 centimeter has been drawn. From this point to any point on the arc, it is always 5 centimeter. So this is our magnitude 10 Newton represented by 5 centimeter on the graph. Now this 5 centimeter is proportional to 10 Newton because 1 centimeter is equal to 2 Newton. Now we need a direction. We'll keep the center of the protector here. I will measure 45 degree from x-axis. Will be at the center from this point, this being 45 degree from x-axis, will touch at this arc at a point. This point is the head of the vector. Let it be P. So F vector is equal to OP vector. So in this way we can graphically represent our vector. So from here we'll remove our arc. From here we'll remove our arc. Now OP vector is equal to F vector. Now in this way we graphically represent a vector. A very important point to notice here is when we graphically represent a vector, we need a strong or a standard reference line, which in one dimensional is x-axis, in two dimensional being xy plane having x-axis and y-axis. In three-dimensional plane we have x, y and z-axis. So this is a two-dimensional plane. So any vectors drawn on this plane are coplanar vectors. Now these vectors can be used as a reference. Let's see an example. Let this OP vector equal to 10 Newton at 45 degree with some reference line. Now this OP vector is 10 Newton at 45 degree with reference to some line. We don't know what is the reference here, but this given vector can be used as a reference for other vectors. Now if we draw a vector here OQ at 45 degree from this vector, it is sure that OQ vector is equal to the magnitude. The magnitude here is proportional to the length. If we measure this length, we can get the magnitude of the vector. So let's consider this being x Newton. We don't know. We can measure and we can put the value here at 90 degree with reference to the same line by which OP vector was plotted. Now this can be used to represent a vector, but it is not the best method to represent a vector. But it is always a good idea to reference a standard reference. So we use one-dimensional Cartesian coordinate system or two-dimensional or three-dimensional Cartesian coordinate system. This way can be represented. It can be done, but it brings a lot of confusion here. So it's better to use a standard reference line or system.